Okay guys, to kick off this next video, I just wanted to say a few quick words about a related type of spectroscopy called electron paramagnetic resonance, or EPR. It goes by the synonym electron spin resonance, or ESR. Those two are the same thing. This is analogous to NMR, but for electron spin flips in the presence of a magnetic field. And so what I've worked out here, which I don't need to cover in any detail, the spin angular momentum gives rise to a magnetic moment for the electron. There is a magneto-gyric ratio for the electron, a electron G factor of about 2. In the presence of a magnetic field, that magnetic moment is coupled to the magnetic field, and you get a splitting of the degenerate spin states for the electron, perfectly analogous to what we looked at for NMR. Again, you can write these in different units. Looking at the resonance condition for EPR, you take the difference in energy between the two spin states that are split by the magnetic field, and you can calculate the EPR frequency for electron spin flips in the presence of a magnetic field. Everything is perfectly analogous to what we had for NMR. In order to use EPR, your molecule or your atom must have an unpaired electron. That makes EPR useful for certain types of transition state complexes. Again, the diagram there is the same. One technical difference is that the EPR spectrometers use a much smaller magnetic field, and the EPR frequencies are often in the microwave range of the EM spectrum. So there are some technical differences, but conceptually at least, EPR is very similar to NMR. So I'm just gonna skip through these details, and we'll go ahead and start the next topic. We'll go back to NMR, focusing on Proton Nmr Spectroscopy. And so we're going to talk about Proton Nmr Spectra. And so this concept here, the chemical shift, this has to do with the fact that the NMR frequency that we discussed in the last video is sensitive to the chemical environment around a given nucleus. So in a molecule, you have different protons. Okay, they're in different chemical environments, and the NMR frequency for those different protons will be different from each other. Okay, and this allows you to identify different protons within the molecule, and that's what makes NMR so useful, is that you can distinguish different types of protons in your molecular sample. And so the idea here behind the chemical shift, what causes this chemical shift? Well, when you apply a magnetic field to a molecule, it causes the electrons in the molecule to move around. They start circulating, okay? And when charge moves around, when you have a current, that creates its own magnetic field. So the circulating electrons in the molecule, in the presence of the magnetic field, creates an opposing magnetic field, such that at different nuclei, the magnetic field experienced by the different nuclei, the external magnetic field will be modulated by this opposing magnetic field that depends upon the electron density in the region of the nuclei. We say that this gives rise to a shielding of the nucleus from the magnetic field, represented by this parameter sigma called the shielding constant. So the magnetic field at a nucleus is lessened by positive values of sigma, right? If you have a positive value of sigma, that's going to decrease the magnetic field that the nucleus feels. Okay? And if the magnetic field at the nucleus is different, then the NMR frequency of that nucleus will be different. and that's what's given here. You will have a shift in the NMR frequency related to the shielding constant for that particular nucleus. So sigma is different for different nuclei within the molecule. The chemical shift is typically measured in so-called ppm units, parts per million. We measure the NMR, the shift in the NMR frequency with respect to a particular standard. So nu-0 here is the NMR frequency for a particular compound. Often in proton and carbon-13 NMR, we use tetramethylsilane, or TMS. And so that's the frequency of your standard. And then the chemical shift is measured as a difference between the frequency of the particular nucleus and the standard divided by the operating frequency of the NMR spectrometer. And then you multiply that by 1,000,000. You can rearrange this equation and solve for the NMR frequency of your nucleus in terms of the NMR frequency of your standard, plus this correction factor here involving the chemical shift. So while the actual radio frequency that causes the nuclear transition depends upon the spectrometer that you're using, that is, it depends upon the magnetic field strength of your NMR spectrometer, the chemical shift, however, I left off the sentence, however, the chemical shift is independent of the spectrometer. And so that's why we report NMR frequencies in terms of chemical shifts rather than actual radio frequencies. It's so that people who are using different NMRs get the same value of the chemical shift. Oh, in this illustration here, you're being asked to calculate the chemical shift for a resonance frequency of 500 megahertz and some change. You're given the operating frequency of the NMR, and then you're also given the NMR frequency for this particular NMR of the TMS standard. Okay, and so you take the expression for the chemical shift and you plug in the resonance frequency here, you plug in the resonance frequency for the standard, divide by the NMR spectrometer's frequency, multiply by 1,000,000. That gives you a chemical shift of 1.5. So no matter what NMR you are using, that resonance will always be at 1.5 ppm. In the follow-up problem, for the same spectrometer, we're being asked to calculate the frequency difference between two resonances at these particular chemical shifts. So it's kind of the opposite of what we just did. You're given the chemical shifts, and then you're being asked to calculate for this spectrometer what is the frequency difference between the two resonances. So you take this same formula, and then you just take nu2 minus nu1. And so you'll have this expression for chemical shift 2 minus this expression for chemical shift 1. That gives rise to this expression here. You just plug in those same parameters plus the chemical shifts that you're given, and then you can calculate the difference between the two frequencies, between the two NMR frequencies in units of hertz. This is an important relationship. It gives us the relationship between chemical shift and the shielding constant for a particular nucleus. Here I've laid out the important rules at work here. So this sigma naught represents the shielding constant for your NMR standard. Okay, and so if you decrease the sigma value, so that is, if there is a smaller value of the shielding, then you're going to have a larger value for the chemical shift. Okay, so if sigma is smaller, delta is going to be larger. Conversely, if you have a nucleus that is very shielded, Okay, so if you have an increase, if you have a nucleus that has a particularly large value of sigma, that's going to cause it to have a smaller chemical shift. So depending upon the amount of shielding on a given nucleus, you'll find the resonance appearing at either larger or smaller ppm values. When we have a large chemical shift, we say that the nucleus involved is strongly deshielded. If you have a small chemical shift, we say that the nuclei is shielded, relative to the standard at least. Electron withdrawing groups draw electron density away from, so let's say you've got a nucleus that's attached to an electron withdrawing group, that tends to pull the electron density away from the nuclei of interest. That ends up deshielding the nucleus, and so that that nuclei will undergo a resonance at a larger value of the chemical shift. Another primary rule in NMR is that the overall intensity of an NMR resonance is proportional to the number of chemically equivalent nuclei. So if you have a bunch of, let's say on a methyl group, you've got 3 hydrogen atoms in the methyl group. They're all chemically equivalent, that is, they're in the same chemical environment. They will each contribute to the resonance. Okay, and so you'll get a resonance that's 3 times larger than you would for just a hydrogen atom by itself. This is a nice table to look at. It shows you the expected chemical shifts for different types of protons in the upper panel and different types of carbons in the carbon-13 spectrum for different chemical environments. So over here we've got an acetic acid proton. We see that it is occurring at a large chemical shift. Compare that to a methyl group, which appears at a much lower chemical shift. And this is, bread and butter for organic chemists, right? They're looking for this kind of stuff to figure out what they've made, to verify that they've made what they thought they made, and so forth. And so this is what makes NMR chemically useful. Here we are being asked to interpret the NMR spectrum for this 1-methoxy-2 propanone structure. Taking a look, so this is probably stuff right from your organic chemistry course, and you can probably do it better than I can. You've got three groups of chemically equivalent protons. So the protons here in this methoxy group, they're all identical to one another. The protons here are identical, and then the protons on this methyl group are identical to each other as well. And then so the question is where will these different protons appear in the spectrum? And so what you want to do is ask yourself, which of these protons is closer to an electron withdrawing group? And then you can also ask yourself about the relative intensities of the peaks. And so in this case, you can see that that these two resonances here, they have an equivalent height. That is, the intensities of the two peaks are the same. And this little bar here represents the integrated intensity. And so the larger that difference is, the more protons you would expect to be contributing to that resonance. And so here we see we've got these two peaks there, they have equivalent resonances, and so that tells us that one of them is associated with this methyl group and the other one is associated with that methyl group. And then we've got this smaller peak here, which we can assume is going to be coming from this group of protons, number 2. The question is which of the two methyl groups here is going to be the one that's occurring at the higher chemical shift. Recall that larger chemical shifts correspond to protons that are more deshielded. And so the closer you have these protons to an electron withdrawing group, the more de-shielded they will be and the larger the chemical shift. Well, in this structure here, you've got the protons attached to a carbon that is directly attached to a very strongly electronegative atom. On the other side of the molecule, you've got a carbon, then an oxygen. Okay, and so these protons are closer to the electron withdrawing group than these protons. And so we would expect that this resonance here corresponds to this methyl group that's attached to the oxygen, whereas the methyl group here is attached to this carbonyl group. And so group 1 hydrogens correspond to resonance A, group 3 hydrogens correspond to resonance B, and then group 2 hydrogens correspond to the resonance C. Well, I think I'm going to stop this video right here.